Welcome to my channel Worldwide. Why are there not more people talking about the U-2 incident and its impact on modern aviation? The Cold War was a time of intense suspicion, a period marked by the constant shadow of potential conflict between the world's two superpowers. With the US and Soviet Union closely monitoring each other, espionage and intelligence gathering became critical components of national security. High-altitude reconnaissance flights like those of the U-2 spy plane were crucial for gathering intelligence from the skies, providing a bird's-eye view of enemy activities. The U-2 flew at altitudes thought unreachable by Soviet defenses, soaring above 70,000 feet until May 1, 1960, when this belief was dramatically challenged. On that fateful day, a U-2 piloted by Francis Gary Powers was shot down over Soviet territory, causing a major diplomatic crisis and exposing the vulnerabilities of high-altitude reconnaissance. This incident shattered the belief in high-altitude invulnerability and highlighted the urgent need for new reconnaissance methods that could evade detection. The U.S. needed aircraft that could penetrate hostile airspace undetected, leading to a significant shift in military aviation strategy. The U-2 incident spurred the quest for stealth technology, aiming to make aircraft invisible to radar, a revolutionary concept at the time. Scientists and engineers were pushed to rethink aircraft design, focusing on reducing radar cross-section, RCS, which determines how detectable an aircraft is by radar. A smaller RCS means the aircraft is harder to detect, requiring a revolutionary approach to aircraft design, materials, and overall structure. The U-2 incident underscored the limitations of existing technology, shifting focus to stealth and the development of aircraft that could operate undetected in enemy airspace. The age of stealth was about to begin, born from a Cold War failure, and it would forever change the landscape of aerial reconnaissance and military aviation. The dream of radar-invisible aircraft existed long before the U-2 incident, with early attempts during WT-2. Engineers and scientists were already exploring ways to make aircraft less detectable by enemy radar systems. These initial efforts laid the groundwork for future advancements in stealth technology. During World War II, various techniques were tested, including special coatings and unique aircraft shapes to reduce radar visibility. However, these early methods were rudimentary and often ineffective. True stealth research accelerated post-U-2, focusing on understanding and defeating radar. The Cold War era saw significant investments in military technology, with radar systems becoming more sophisticated and widespread. Radar sends waves that bounce off objects, revealing their location. The challenge was to create aircraft that could either absorb these waves or redirect them away from the radar source. Stealth technology aims to minimize or redirect these reflections. This involves not only the shape of the aircraft but also the materials used in its construction. Engineers experimented with various materials that could absorb radar waves, as well as innovative design techniques to scatter radar signals. This meticulous process required extensive testing and refinement. In the 1970s, Lockheed Skunk Works developed Echo-1, a program predicting radar returns from shapes. This groundbreaking research allowed engineers to design aircraft with significantly reduced radar signatures. This led to the HAV Blue program and the F-117 Nighthawk, the first operational stealth aircraft. The F-117's unique design and advanced materials made it nearly invisible to radar. The F-117's faceted design deflected radar waves, proving stealth's practicality. Its success demonstrated that stealth technology could be effectively integrated into military operations. Stealth development involved advanced mathematics, materials science, and engineering. Each discipline played a crucial role in overcoming the challenges of radar detection. Soviet physicist Pyotr Ufimtsev's work on radar reflections was crucial, studied intently in the US. His theories on electromagnetic wave scattering provided the scientific foundation for modern stealth technology. The journey from the U-2's vulnerability to operational stealth aircraft like the F-117 was a testament to ingenuity. It showcased the relentless pursuit of innovation and the collaborative efforts of scientists, engineers, and military strategists. The B-2 Spirit bomber represents a significant evolution in stealth design beyond the F-117. Its smooth, flying wing shape is inherently stealthy, lacking large vertical surfaces that reflect radar. The B-2's wings blend seamlessly into the body, creating a continuous, curved surface. This design deflects radar waves in various directions, minimizing detection. The B-2's shape is engineered to scatter radar energy, with swept-back leading edges and a sawtooth trailing edge. Engine intakes are on top of the wings, S-shaped to shield from radar. Exhaust nozzles are buried within the wing, reducing radar and heat signatures. The absence of a vertical tail reduces side aspect radar signature. Split rudders on the wing provide yaw control without compromising stealth. The B-2's shape is a masterclass in radar evasion. The B-2 Spirit's stealth relies on its shape and advanced materials. Radar-absorbent materials, RAM, absorb radar waves, converting them to heat. The B-2's skin is a complex sandwich of carbon-based composites, lightweight yet strong. These materials absorb radar across a wide range of frequencies. The exact composition is secret but includes ferrite particles in a polymer matrix. The B-2 is covered in special coatings for additional radar absorption and surface smoothness. The coatings may also reduce infrared signature. Maintaining these coatings is complex and costly, requiring climate-controlled hangars. The combination of shape and materials makes the B-2 hard to detect, with a radar cross-section like a large bird. While radar invisibility is crucial, the B-2 also evades infrared detection. Heat-seeking missiles target hot exhaust plumes and surfaces. The B-2's engines are buried within the wing, shielding heat from view. Exhaust gases mix with cool air, lowering temperature. Over-wing exhausts spread cooled gases, dissipating heat. The B-2 flies at high altitudes where cold air cools the aircraft. Special coatings may reduce heat radiation. The B-2 avoids afterburners, minimizing heat visibility. Internal heat management systems distribute and dissipate heat. The goal is a cool signature, enhancing survivability. The B-2 Spirit is a formidable strategic bomber with intercontinental range. It can fly 6,000 nautical miles on internal fuel, reaching global targets. Aerial refueling extends its range indefinitely. The B-2 carries up to 40,000 pounds of ordnance in internal bays, maintaining stealth. It delivers conventional and nuclear munitions, including JDAMs and bunker busters. The B-2 is a key component of the U.S. nuclear triad. Its precision targeting minimizes collateral damage. The B-2's combination of stealth, range, and payload ensures few targets are beyond reach. The B-2 Spirit's primary defense is stealth, but it also has advanced electronic countermeasures, ECM. ECM systems detect, deceive, and jam enemy radar and missile guidance. If detected, the B-2's electronic warfare systems enhance survivability. The B-2 likely has advanced radar warning receivers, RWR, for situational awareness. RWR data cues defensive systems, directing jammers to threat radars. Active jamming systems transmit signals to confuse enemy radar. The B-2's jammers adapt to different frequencies, effective against various threats. ECM may include countermeasures against infrared missiles like flares or DIRCM. The integration of stealth and electronic warfare makes the B-2 resilient. The B-2 Spirit first saw combat in Kosovo in 1999, flying from Missouri. This marked the beginning of its storied operational history, showcasing its ability to project power across the globe. It delivered precision munitions against Serbian targets, demonstrating global reach and pinpoint accuracy. The B-2's ability to strike with such precision was a game-changer in modern warfare. Despite flying less than 1% of sorties, B-2S dropped 11% of bombs during the conflict. This efficiency underscored the bomber's strategic value and effectiveness in high-stakes missions. The B-2 operated with impunity, penetrating dense air defenses that would have thwarted other aircraft. Its stealth capabilities allowed it to evade radar and deliver its payload undetected. In Afghanistan and Iraq, B-2S flew long-duration missions, striking key targets with precision. These missions often lasted over 40 hours, showcasing the endurance and reliability of the aircraft. In 2011, B-2S participated in Libya, targeting air defenses and critical infrastructure. Their involvement was crucial in establishing air superiority and supporting ground operations. The B-2 program is expensive, with each aircraft costing over $2 billion. This high cost has been a point of contention, but the capabilities it brings are unparalleled. Only 21 B-2S were produced, leading to debate over costs and production numbers. Despite this, the fleet remains a critical component of the U.S. Air Force. Maintenance is complex, requiring specialized facilities and highly trained personnel. The upkeep of these bombers is essential to ensure their readiness and operational capability. Despite costs, the B-2 remains vital, unmatched in penetrating defenses and delivering payloads. Its ability to refuel mid-air extends its range, making it a versatile tool in the U.S. military arsenal. It serves as a powerful deterrent and cornerstone of U.S. nuclear strategy. The B-2's capability to carry nuclear payloads ensures it remains a key player in maintaining global stability. The B-2's stealth, range, and firepower ensure continued relevance in an uncertain world. As threats evolve, the B-2 Spirit stands ready to meet them, securing its place in the annals of military aviation history. Watch my next video now.